This is a classic curve called Gabriel's horn. That's a section of y equals 1 over x. So technically, Gabriel's horn goes all the way off to infinity, but we have enough of a chunk here to look like a horn. And we're trying to do kind of everything for this. So I want the arc length of this curve. And then when I actually create the solid of revolution, I want the volume of the solid, and I want the surface area of that solid. So we're kind of putting all these applications together. So to get the arc length, I have f of x is 1 over x. I know that I'm going to need f prime, so I'm just going to compute it right here. F prime of x is negative 1 over x squared. And then my arc length integral looks like, I guess I'll use this. Integral as x goes from 1 to 10. Square root 1 plus this derivative squared. So it's 1 over x to the 4th dx. So if I go into a computer algebra system, and I'm going to go to Wx maxima, and I try to compute this, maxima just gives me back the same integral, which means it couldn't find a way to do it symbolically. So we're going to have to use a numerical approximation on this. And that's quad QAG, and this function requires that you pick one of the algorithms from number 1 through 6 that's built into maxima. I usually choose algorithm number 1, but I'm just going to mix it up and choose algorithm number 2 this time. You're going to get the same answer essentially to many, many decimal places, so I normally don't care. So I get 9.15 on this. For that arc length, which is plausible because the horizontal distance from here to here, from 1 to 10, that's 9. And this is a curve that's pretty flat, so I just get a tiny bit more than 9. Makes a lot of sense. Okay, let's get the volume of Gabriel's horn. And it looks pretty natural here to slice into discs. So there's a nice disc. It has a thickness of dx. The radius of the disk, so this dimension, is just the distance between the y-coordinate on the curve and the x-axis. So that's just the y-coordinate, 1 over x. And then I can write down a differential volume for a disk. So I'll call that dv, and that's going to be the area of a face here on the disk, pi times the radius squared, multiplied by the thickness of the disk, and then I use an integral to add up all those dv's. dv is entirely phrased in terms of x, so we're ready to go, and we're integrating from 1 to 10. I have pi times 1 over x squared dx. And so I can guess the antiderivative pretty quickly on this. That's x to the negative 2, which integrates to negative 1 over x. So I end up with pi times negative 1 over x, evaluated from 0 to 10. And when I plug in the 10, I get negative 1/10 pi. Then I subtract the result I get when I plug in, oops, that's not a 1. I mean, it's not a 0, it's a 1. When I plug in the 1, I end up with a positive result, and that's just, this term becomes 1, and I just get pi. So that looks like 9/10 pi. Let's get the surface area of this Gabriel's horn. So I'm going to mark out a little ribbon that I want to cut out of the surface. So it's important when we're doing surface area to use ds, a little section of arc, for the thickness instead of dx. And I'm going to slice and unroll this thing. Maybe before I do that, I'll just write down the radius of the ribbon. It's the same as the previous part. The distance here is just 1/x. So I'm going to slice and unroll this little ribbon. And lay it out flat. And the length of that is going to be the circumference of the ribbon that it came from. So that's 2 pi times the radius, or 2 pi times 1/x. The thickness is a little ds, a little arc element. And remember, that comes out to this expression that we used to add up all the arc a minute ago. 1 plus 1/x to the 4th. And now I can write down this infinitesimal area contribution. dA is going to be 2 pi times 1/x. Square root 1 plus 1/x to the 4th dx. So now I can use integration to add up all those dAs. Okay, and interestingly enough, it turns out this integral has a symbolic solution. I haven't even attempted it by hand, but let's go over to Maxima and check out what it looks like. So I plugged in and I said integrate this thing because I was curious if it had a symbolic solution. And press Shift Enter, and I get that exact symbolic solution. Looks like it must have been a pretty hard integral. I could get a decimal approximation for this just by using the float command, or I could go back to the beginning and change to quad QAG to just use a numerical integration technique. But since it came out in exact form, I can go ahead and use float. So 15.2-ish, I'd say, is good enough.